Okay. So, hello everybody, my name is Christopher Taylor.
I'm Jonathan Fernandez.
Marshall Taylor.
And Dominic Garcia.
And today we actually have a recycle bot that we're going to be showing you. So, for our presentation, we actually had an initial concept originally. I'm sure some of you have seen the presentation before and know this. Our idea was based off of the Roomba. It's going to go around, pick up stuff inside your home. The same idea, however, outside. We wanted to pick up trash and bottles from outdoor venues and bring it back to a home base that will actually sort everything. The biggest thing with our project is meant to address the issue of not recycling. Large concerts are held and all they care about is picking up the trash. They don't actually sort the items, all they do is clean up and get out. And that right there is a problem because, as we've all seen, recycling helps a lot. And in order to address the need of actually recycling everything, we decided to design this project. So, we actually have revised our concept. Initially, we started it with being a trash bin, almost kind of similar to these ones over here in the corner, or right here that's entirely visible. We also decided to think about an actual usage of it in some places like Disneyland as a theme park. Rather than having something that stands out that everybody can see, we wanted something that's a little bit more hidden. And actually, we decided to try and implement having this go underground, if you will, with an ability for the robot to just sweep around people and drop it off in a safe location. This way, it's out of sight and out of mind. So each of us had our own tasks. I was actually in charge of the home base unit.
I was in charge of the robot and the motors.
I was in charge of the image tracking to get it back to home base using the Pixcam.
I was in charge of the image processing using a Raspberry Pi and a PiCam.
I was in charge of the circuitry with the robot and the home base. Alright, so for IR and sonar signal processing, so we're using infrared sensors for collision avoidance, but we're actually using the sonar ultrasonic sensors. We have 3 of them in the front and we have 2 of them on the side. So what the robot's gonna actually do is it's gonna read each sensor value and determine if it can go forward, if it can go slightly left forward, slightly right forward, if it can make a right turn or a left turn, or even go backwards, just depending on what obstacles there are.
So for the image processing, like I stated earlier, we used a Raspberry Pi, a PiCam, and OpenCV. Our main goal was to detect 3 different types of materials, which were glass bottles, plastic bottles, and aluminum cans. However, we ran into some problems because the plastic bottles and glass bottles were transparent. So as a result, we were getting false positives. The main reason I think this is because as you take a picture of something that's transparent, you pick up things in the background, and they were, when we would take a picture with the PiCam for the image detection, it would pop up on the screen that something wasn't there, even though we wanted to detect it. So the PiCam and the Raspberry Pi go into the home base. It goes into the home base right here, so the robot will go out and pick up a whatever glass bottle that we can, and it would dump it into here. Once that was done, the Raspberry Pi would take an image of it and detect whether what type of object it was. Once that was done, the Raspberry Pi would send a signal to an Arduino to tilt the studio, and then it would send another signal to the.
We have like the sorter bin over here.
Yeah, so it would rotate precisely to if it was waste, aluminum, glass, or plastic. And, yeah.
So for the main brains of the actual robot itself, we use an Arduino Duo. It controls all the signals. Initially, we started off with a Raspberry Pi. But then we were getting troubles with the UART and the SD card always being corrupted, and we would have to restart everything all over the programming. So I decided to go ahead and use 2 Arduino Unos, one controlling the motors, one controlling the sensors. And another problem I ran into was actually it reading the UART communication at the right speed. So I decided to move over to the Arduino Duo. It has 54 pins. And it has a good amount of pulse width modulations and a lot of digital inputs and outputs, and various forms of UART if we need it. And since we're using ultrasonic sensors, we're gonna need 2 pins per sensor, so it's already 10 pins right there. That's practically one whole Arduino by itself. And not to mention, we're also controlling the motors, which is around 6 pins. So this is more ideal for us. And it has a faster processing chip, and it is also more, since we have everything all in one microcontroller, we don't have to wait until another signal comes in. We can just do it automatically, and we'll have less errors actually doing it. So we're using the tool H-bridge motor controllers just to drive them, just using tool H-bridges, controlling 4 motors.
Okay, so for my part, I was doing the image tracking. So like Chris was saying, we wanted the home base design to potentially be underground. So all we really needed to do was maneuver it towards there and drop the object in. So with PixieCam, what it's able to do is determine distance from the image as well as orient itself properly. So for our code, it's able to determine the x-axis depending whether or not the image is in the proper location via that way. And then it can also detect a width and height, which will calculate an area and determine whether or not it's in the correct parameter, and then move forward and backwards to make sure it's within the correct threshold.
So we have a video actually of that working. So here we actually have it looking for the ball right now. And it's a little jittery only because the actual data transfer from the PixieCam to the motors itself is not able to actually control the motors itself. It's a little bit of a delay. So rather than having it constantly go at full speed forward and then stop at the last second running into the object, we decided to have it just do little jitters until it parked itself right where it needed to.
Yeah, so with the problem with that was that if we left it on full speed, it would go either too far, forward, backwards, left, right, and then it would just keep repeating itself back and forth so that it would never properly orient itself. And then if you saw in that video, we kind of integrated it so that we made it so once it finds the proper location, and then per se, if we had the arms on there, it would drop the object and then go into the routine where it would continue to go around with the ultrasonic and try to find the object and to avoid walls and whatnot.
Okay, so this is the, that was the chassis. So this is the chassis that we have right here. It's a fully modular metal chassis with all-terrain wheels. So the idea of this was to be a Roomba that can be used in outdoor purposes. And so this would be perfect. We actually tested this and we went over hills and bumps and through sandy terrain. We really like this because originally it was a lot smaller than this. And then we added the second layer, and then we added another bed right here so that we can house more of the Arduinos. And then also we started to do these 3D printed sensor housings because we originally had 2 up here, but then we saw that it had blind spots in front of the wheels. So we created these to cover those blind spots. And as you can saw in that last video, it was about to hit that corner, but then it caught it and then it made that turn. So the sensors are, when they send a signal, and then they'll receive a signal, and then it'll go through a function to either turn left or right or to turn around.
So right now it's currently trying to find any of its bearings, I think.
So the problem with this was that lighting was a big issue. So we tested it in the upper rooms where it had different lighting. So in here it might not be able to catch the object as easily. So right there, this time it actually caught it because it was a bit closer. And now it's trying to orient itself properly. And once it finally gets to the right spot, boom. Now it's going to go lay and then it's going to the object.
Picking up trash.
So So this is actually running through a maze that we had designed ourselves. And at first it gets a little disoriented. This is before we actually 3D printed the new sensor case. So this is when it was still running into everything, having those blind spots. But it's able to actually determine where it needs to go and move forward or around and everything. It actually works pretty fast in terms of how quickly it processes everything, which is optimal for us going out and picking up cans and what other objects. So the home base unit, as I said, we had an initial design of having it be available as a trash can, and we use an elevator feeder system to drop everything into a studio. Rather than keeping that, we ended up actually also implementing it as the underground version, which we see right now. Our original demo was planned to be on the table so that you could see that. However, we did run into some complications just integrating everything. We found that we were able to actually power the home base using a PC power supply. However, the problem that we faced was that the power supply itself, if we added too much of a load on it, even though it's able to withstand it, it would actually force itself to turn off as a surge protector. So we actually encountered that multiple times in trying to redesign our circuit and make it more functional. However, the home base unit as a whole, as they mentioned, was meant to hold the bottle in the studio. The bin would rotate to the proper partition depending on what the item was, and actually dump it in there and be able to receive multiple objects. In actual application, we would have an elevator queue system similar to a construction digger, if you've ever seen any of those. It actually would hold each individual item and raise it and dump it in as it was needed to. So again, we had the two designs that we were considering, an underground one and the visible one. And again, it does look like both. We did choose cardboard as our base only because we wanted something that was cheap, flexible, easy to work with, and in the event that we use this for quick deployment in a concert venue, it's easier to just recycle everything itself and actually not have to worry about trying to reuse it. The idea was that we could actually design this in a cheap method so that it wasn't cost heavy in terms of actually having to buy a new unit if it ever broke, rather than trying to scrap everything as we've seen with a lot of e-waste.
So speaking of cost, this is our original budget idea here. The price that we have here is, and the equipment that we were expecting to buy is really different from what we have. Originally we thought we were going to get treads. We're going to do like a tank style to move it across the terrain. And we were going to originally use like connects or like PCB pipe to make the chassis. But, and then the total is going to be $651. But if you go to the actual, it would end up being about $40 less because we did have a lot of contributions from IEEE. That whole metal chassis right there was, and the wheels was from them. So we got that for free and we saved a lot of money there. And we did a lot of trial and error here too, that kind of brought up the price. But in the end, we ended up being under our budget. So, yeah.
Any questions? Yes.
I think you guys have done a fantastic job, and to take you guys off the hot seat for a minute, I actually have a question for your advisor. Hey, Kieran, I got a question for you.
Oh. Yeah.
So, I'm seeing some really fantastic technology developed here, and capabilities, knowledge, and so forth. It's amazing for projects. But I'm thinking, how do we get this to the next level? Right? So I'm thinking, how do you take, standing on the shoulders of giants kind of philosophy? How do you take what these guys have learned and what they've built, pass it forward to another set of students so they can build on that, and then build on that, and build on that? And then how do we bring in, say, some students from the business school, for instance, to start looking at maybe market opportunities and more, I think there's some technology here that would be super beneficial for the university. And eventually, intellectual property licensing and providing funding back to the university for more future projects. UCI, for instance, the Beckman Laser Institute there, they have laser stuff that was originally developed by faculty and staff and students, generates a $15 million a year revenue stream for the university, and a lot of that goes back to the engineering department for students like you guys. And that's, pretty big money. But, so the question is, how do we take what these guys are doing and pass it forward so the next team doesn't have to start from scratch, and do that over and over, build it up, and maybe bring some guys in from the B school and start pitching companies to license this technology and start generating revenue streams for the department?
we have, again, it's not done in a very structured manner. Very organically, we have often teams working with business students. For example, we have I have Philip from the incubator here,
Right.
and we have a team who worked with business students, came up with a business plan. They won the first prize in the competition. So they have 5K for the incubator. So it is not structured, done in a very structured manner. I would love to have it, done in a structured manner, but that's something. I hope the dean and the president was here. We don't have an IP place where we could file for IP. That's all in the progress. We will. I'm hoping the university will be heading in that direction where you have this later on moved into a team that moves into an IP and all that. So
Okay.
we are not there yet, but we are making steps, taking baby steps there.
Right, so we're meeting at 3 o'clock today to talk just about this. I'm willing to help. I think there's probably people here. And heck, I'm sure you guys would like some money for doing fancier things in the projects, and I think it's there. It might take a little while, and, a couple of classes beyond you guys might get the most benefit for it, but hey, pay for it, right?
Indeed.
Any other questions before we move on? Yes?
One quick question. So use the Raspberry Pis and those kind of small little computers. If your trash collector is bigger size, will you be still able to do the same kind of project using Raspberry Pis, or will you need something bigger? This is something beyond your project probably.
So that depends entirely on, of course, where it's used. If we were to assume like a dumpster size, let's just say that they use a collector that large, then we do have the option of actually using larger computing processes. However, our idea was to use smaller microcontrollers or computers, such as the Raspberry Pi, due to their low cost and high ability to compute. If we did need a larger computer, though, we could, of course, use that, and under the assumption that we could use the Arduino Mega or the Arduino Duo as well, as those are larger ones than the Raspberry Pi. As you saw, I think it was Prakashan's group with the Titan Hyperion. They did have the larger processor as well that we could even incorporate ourselves if need be. Yes?
I have a size-related question too. So given that you wanted to do this to collect recycling, glass bottles, things like that, how big, if you were to do the next prototype, how big would the trash base be in your mind, and how big would the unit be that's driving around picking these things up?
So the unit itself would actually be a similar size to what you saw today, maybe a little bit wider on the base to support a higher load. Maybe change out the motors, of course, depending on the weight. However, we would rather have it that it be a taller unit, of course, depending on where it is implemented. If it was implemented at Disneyland or anything like that, we want a smaller unit so it's peace of mind that it's not highly visible with a high foot traffic. But of course, it being a modular design on the robot itself that goes out and picks up everything, we have the ability and flexibility to change the design as needed. As for the home base itself, it would be closer to a dumpster perhaps in one area. The other option would be that we extend the queue system so that it has a higher delivery rate to something like a dumpster, of course. So it actually takes away from having a dedicated unit and focuses more on the movement.
And how many then, if you have it the same footprint but taller, but how many recycled items do you anticipate is going into it before it needs to go to this dumpster?
So again, that also depends on, of course, where it's being used. The big three, of course, being aluminum, glass, and plastic. We have the ability to incorporate other recyclable materials such as paper, cardboard, styrofoam, organic compost trash versus regular trash for landfills, and move forward on actually expanding the repertoire. We only chose these three because it was the easiest to work with for this presentation, but the sky's the limit in terms of whatever we're able to actually have the image processing work.
And with that, we're going to move on to the next team.